As we've been enjoying and progressing through these videos, we've identified how the routing table is built, meaning how the router decides if it has two or more routes for the same network, which one it should put in its routing table. And we've used administrative distance and the metric or cost as decision points in that process. Now, once the routing table is built and a packet comes into the router looks at that destination IP address and then looks at its routing table to see if there's a match. And then the question is, to route or not to route? That is the question. So what I'd love to do in this video and lab is I'd like to go ahead and look at a routing table on router 3 in our topology, and then compare that routing table to an incoming packet and see if we can predict, based on what we know so far, about what the router is going to do with it. Is it going to route it? And if so, which route is it going to select? Or is it going to drop it? So let's take a look at our topology, and then we'll look at the routing table. So to have some fun with this, let's do this. As we play this game called Will I Route or Will I Drop, let's go ahead and use R3. And as we focus on R3, let's take a look at its usable interfaces. There's really only 4. It can send a packet this way, it can send a packet this way, or this way, or this way. So no matter how many routes it knows about, the egress or outbound interfaces are going to be one of these 4. So for this fun scenario, let's imagine that there's packets that are coming into R3, and in each of those respective packets, they're using these destination IP addresses. So there's one packet with this destination IP address, another packet with this one, and the list goes down. So what I would love for us to do is to take each of these destination IP addresses one at a time, and then compare that to the routing table here on R3, and then answer this question. Is this going to be routed, or will it be dropped? And if it's going to be routed, let's go ahead and choose the route from the routing table that would be used. And once we choose that, we can also verify it by doing a show IP route with that destination IP address, and that will give us more information on the route that was matched. So this is a hands-on lab. So click the link for the virtual lab. Let's open up a console to R3, and let's answer the first question. What happens when a packet with the destination IP address 10401 comes into the router? What will the router do? And if it's going to route it, which route will it choose? So we're going to open up a console to R3 on our management computer. And here on R3, we'll do a show IP route. And we can look at the whole routing table, or we could filter it out with just OSPF routes or the 10 network and so forth. But let's look at the whole thing, starting off with the show IP route. Press enter. And then we'll hit enter a few more times until we can see the networks in question here. So we have a whole bunch of 10 networks. And let me also point out that this E1 represents an external route. So it's OSPF, but it's an external OSPF route. And the reason that's there is because I had to surgically inject a whole bunch of these really cool routes for the purposes of education in this nugget. I injected those routes, and that's why they show up as an E1, an external type 1 OSPF route. And our focus in this nugget is to take a look at the routing table, and then based on the destination IP address, try to predict which of these routes, if any, would be used by the router to forward a packet to the destination IP address. And our first packet we're comparing against is 10.4.0.1. And so because these are all sorted, I would imagine that we're going to start looking somewhere in this range because they all start with 10.4. And then my question is, based on what we learned in the previous videos as part of this skill, if there's multiple routes, multiple prefixes in the routing table for a specific IP address that match, which one is the router going to use? And if you're thinking back on those videos and thinking, Keith, I remember you saying it is the longest match. You're spot on. That is absolutely right. So I suppose the question then is, if the destination IP address is 10401 and it matches all of these, which it does, all these 10.4 networks would be a match. The 17 bits, the 20 bits, the 23 bits, and so forth, all of those are going to match on this IP address. So if we take the process of the longest match, our prediction would be, it'd be this bad boy right here, the 30-bit network, 10.4.0 with a 30-bit mask using 10.13.01 as the next hop. And the next question is, well, how do we verify that? We can verify that by simply doing a show IP route, plugging in the IP address of 10.4.0.1 and see whether or not it's this exact 30-bit route that is specified that the router is going to be using. That's the router telling us, yes, your prediction is correct. So let's do it. So I'm going to hit a key other than space or enter to stop the scrolling, and we'll do a show IP route for 10.4.0.1 and press enter, and survey says, look at that right there. The route entry for 10.4.0 with a 30-bit mask, because it's the longest match, boom, it's the winner. Fantastic. So this gets easier and more comfortable the more you do it. But the goal here is to predict based on the routing table, which route the router will choose to use as it makes a forwarding decision for a given packet. Now, our next question is regarding what does the router do if it gets a packet for 10404? Which route, if any, will it choose from its routing table? Let's take a look at the routing table and make that prediction. So here on router 3, if we do a show IP route, and let's just include the 10 networks. So 10.0.0.0, press enter, and a space bar. And let's jot out the target address, which is 10.4.0.4. Now the question is, which of these routes are going to be a match? And visually, what I can see is that the first 24 bits here, 1040, match all of these, the first 24 bits at least. So I know that at least the first 24 bits match exactly in all these routes. But where it gets dicey is that last octet, especially as we get into masks that are longer than 24 bits. So I think that /26, /29, and /30, we might want to check those out just to verify whether or not they match based on this destination IP address of 10.4.0.4. So if we build our table regarding the values of the 8 bits in an octet, 128, 64, 32, 16, 8, 4, 2, 1. And the reason I'm chuckling is because even as a double CCIE, I encourage people, if they're just learning it, to do this. And if I want to double check my work on something or validate something, if I'm not using a subnet calculator, I will literally draw these out just to confirm that my logic and thinking is correct. So it's a great way to start out. It's also a great fallback if you ever need to verify, does an IP address live in this subnet? And let's put in the masks for /26, /29, and /30. And this will be our 4th octet. So I will label this column here as masks. And the mask we're looking for is 26, and then for 29, and then for 30. So a 26-bit mask would look like, here's the 24-bit marker right there. It'd be 24 plus 25, 26. Boom. All the rest would be zeros for the mask. For 29, it'd be starting at 24, 25, 26, 27, 28, 29, just like that. Great. And the rest would be zeros. And for a 30-bit mask, it'd be starting at 24, 25, 26, 27, 28, 29, 30, and then the rest zeros. So with this information, if this is the least significant bit of the mask for a /26, the block size for those networks is going to be 64. For the 29-bit mask, the least significant bit here is a value of 8, and that's going to be the block size. And for a /30, it's here, and so that's going to be a block size of 4. So for a 26-bit mask, using these first 3 octets of 1040, for the /26, it's going to be 10.4.0. That doesn't change. And for this 26-bit network, it's showing the last octet of all zeros. So it would show up as 10.4.0.0, just like it does right here. And then the next subnet, if we were going to add the next subnet, would be 64 more in that last octet. So this is the subnet we're looking at. The next subnet would be 64, and then the next one would be 64 more, and so forth and so on. So the range for the IP addresses in this subnet would be 10.4.0.1, because you can't use the all zeros for host bits, and the last one would be the next subnet -2. Because the one just below this subnet is this subnet's broadcast address. So that's the last usable address on that subnet. So that's the range, 10.4.0.1 through 62. So this packet right here, 10.4.0.4, is definitely going to match on that network, the 10.4.0.0 network with the /26. That matches. Great. So we know that this is in. I'll circle that as a winner. Let's check out the /29. So for a /29, the block size is 8. So it would be 10.4.0.0. But with a block size of 8, the next subnet would be 8. And then the subnet after that would be 8 more, 16, and so forth. So the range for the /29 network would be 10.4.0.1 through, and then 2 less than the next subnet, which would be 6. So the 10.4.0.4 is definitely also in that range. So we can go ahead and say that's a match as well. So based on just these 2 routes, the /29 is a longer match for this destination IP address. And let's do one more for the /30. So a /30 has a block size of 4, and that means, I'll put the /30 up here. That means that the /30 is going to be 10.4.0.0. And the next subnet would be in that 4th octet, .4, and then 4 more, .8, and then .12, etc., adding 4 and 4 and 4. So the range for the network 10.4.0.0 with a 30-bit mask would be .1 through, and then 2 less than the next subnet, through .2. And that's it. And if we look at our destination IP address, it does not fit in that subnet. And as a result, this route, the /30 route, would not be a match because it does not match, this IP address does not match the first 30 bits associated with this 30-bit route here we have in the routing table. So that means our winner for the longest match would be 10.4.00 with a /29 based on this longhand math that we just did to verify that. Now the question may come up, well, how do we verify that that's really the route, that /29 is really the route that the router is going to choose based on that destination IP address? And the answer is, we just ask it, show IP route, and we plug in that IP address of 10.4.0.4, and it will show us the exact route it chose from its routing table. Let's take a look. So we'll do a show IP route space, and we'll put in 10.4.0.4, press enter, and sure enough, now the reason I'm chuckling is because it made that decision light years faster than we did longhand. But it's important for us to understand how it's choosing that route by making sure that the routes it has is being compared to that destination address, and then based on all the matches, choosing the longest match. So for a packet going to 10.4.0.4, it would use this route, and that route right here is using the next hop of 10.13.0.1 and the exit interface of gig 1/0. And that route was learned via OSPF. It has an administrative distance of 110, and the metric for that route is an OSPF cost of 4. So in this video, I structured it so we could cover a couple of specific things. Number one, I wanted to go through the process that the router's using as it looks at an incoming packet, considers the destination IP address, looks at its routing table, and chooses the longest match. The second thing I wanted to do was to walk you through the process of identifying, based on looking at an IP address, which prefix or which network would match. And to do that, we had to go to binary a little bit. Now, some of you might be thinking, well, Keith, I didn't realize we're going to have to go to binary for this and have to do some calculations. And the answer is yes. It is important to understand how that works. And in previous skills that we covered with Jeremy, he walked you through the steps of setting up and working with subnetting and how that operates. If you need to revisit that, please do so. We also have another course on just IPv4 subnetting here at CB2 Nuggets that can also be useful. So here's what I would encourage you to do. In this video and lab, I would encourage you to watch this video at least once or twice. I'd encourage you to do the hands-on practice as you show the IP route, calculate which subnet based on the routes that are in the routing table that destination IP address belongs to. And we're starting off with just two IP addresses, two destination IP addresses, 10.4.0.1 and 10.4.0.4. So after you've had the opportunity to go through this video a couple times and maybe do the longhand practice for identifying, okay, based on this IP address, which routes does it fall into, we're going to take it to the next level in the next video where we'll do just more than two specific IP addresses. We'll do 5 or 6 so we can have additional practice in predicting what the router is going to do as a packet comes in and it's looking for the longest match. And the benefit of doing this is that we don't just have to blindly hope the router is going to forward packets in the right direction. We can do the calculations and we can figure it out and predict what the router would do. And that's going to help us a boatload, because in a production environment with lots of routes and packets that may not arrive or may not be delivered, we need to have the skill of being able to predict and identify which routes in a routing table the router is going to choose. So these labs and exercises that I've designed are here to help assist in building those skills and becoming better and better at using them. So I'll see you, my friend, in the very next video and lab. Meanwhile, I hope this has been informative for you, and I'd like to thank you for viewing.